students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 11th physics system of particles and rotational motion. Chapter 7 ncert solution part 3. Before we begin, we request you to subscribe, like and share our YouTube channel among your friends and relatives. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Let us begin today's class. In the last session, we have done till question number 7.10. In today's session, we'll start with 7.11. Torques of equal magnitude are applied to a hollow cylinder and a solid sphere, both having same mass and radius. The cylinder is free to rotate about its standard axis of symmetry, and the sphere is free to rotate about an axis passing through its center. Which of the two will acquire a great angular speed after a given time? Greater angular speed. So which of the two will appear a greater angular speed after a given time? So this is the question. Let us see the solution. So we'll solve this sum in two steps. First we'll find the moment of inertia, and secondly we'll find the we'll equate the torque for both the bodies and find the ratio of the angular acceleration. So let us see the first step. Let m and r be the respective masses and of the hollow cylinder and the solid sphere. So the moment of inertia of the hollow cylinder about its standard axis is I1 mr square. So one correction here, m and r be the respective masses and radius of the hollow cylinder and the solid sphere. So in that way, moment of inertia of the hollow cylinder is about its standard axis is I1 is equal to mr square. Moment of inertia of solid sphere about an axis passing through the center is I2 is equal to 2 by 5 mr square. In step 2, equate the torque for both the bodies and find the ratio of the angular acceleration. So we have the relation tau is equal to I alpha, where alpha is the angular acceleration, tau is the torque, and I is the moment of inertia. For the hollow cylinder, tau 1 is equal to I1 alpha 1. For the solid sphere, tau 2 is equal to I2 alpha 2. Now, an equal torque is applied to both the bodies. So tau 1 is equal to tau 2. So putting the value of tau 1 as I1 alpha 1 and putting the value of tau 2 is equal to I2 alpha 2, we get I1 alpha 1 is equal to I2 alpha 2. So we can again write I2 alpha 2 is equal to I1 alpha 1, then alpha 2 upon alpha 1 is equal to I1 upon I2. So alpha 2 upon alpha 1 is equal to mr square upon 2 by 5 mr square, which we have put the value, where we have put the value of I1 and I2. So alpha 2 upon alpha 1 is equal to 5 by 2. Therefore 2 alpha 2 is equal to 5 alpha 1. Therefore alpha 2 is greater than alpha 1. This is equation number 1. Now step 3, derive the expression for angular acceleration. Now we use the equation omega is equal to omega naught plus alpha t, where omega naught is initial angular velocity, t is the time of rotation, omega is the final angular velocity. For equal omega naught and t, we have omega is proportional to alpha. From equation 1 and 2, we can write omega 2 is greater than omega 1. Hence, the angular velocity of the solid sphere will be greater than that of hollow cylinder, solid sphere. So, this is the answer, but let us see the important point how we have solved it. So, first thing is we have to find the moment of inertia. So, we have found I1 is equal to mr square and I2 is equal to 2 by 5 mr square. So, I1 is for hollow cylinder and I2 is for the solid sphere. Second step is the torque. Torque is equal to I alpha. So tau 1 is equal to I1 alpha 1 and tau 2 is equal to I2 alpha 2, and we know it is given that tau 1 is equal to equal torque is applied, so we can equate tau 1 is equal to tau 2, and putting the value of I1 alpha 1 is equal to I2 alpha 2, and we found the ratio of alpha 2 and alpha 1 and put the value of I1 and I2 which we have found at the beginning, and we get mr square upon 2 by 5 mr square, and upon solving we get 5 by 2. So we found a ratio of alpha 1 alpha 2 which gives as 2 alpha 2 is equal to 5 alpha 1, which says that alpha 2 is greater than alpha 1. Now the third expression is derive the expression for angular acceleration. So it is simple angular velocity equation. So omega is equal to omega naught plus alpha t, and if for equal value of omega t and t, we get alpha is directly proportional, omega is directly proportional to alpha, and therefore we can, from equation 1 and 2, we can write omega 2 is greater than omega 1. Therefore the angular velocity of the solid sphere will be greater than that of hollow cylinder. So let us move to the next question. Our next question is question number 7.12 or 7.12. The question is a solid cylinder of mass 20 kg. First is solid cylinder, then mass is 20 kg, rotates about its axis with angular speed is also given 100 radian per second. The radius of the cylinder is also given, that is 0.25 meter. What is the kinetic energy associated? So we have to find the kinetic energy associated with the rotation of cylinder. What is the magnitude of angular momentum? We have to find the angular momentum of the cylinder about its axis. So let us see how to solve this one. So the sum is solved in 4 steps. So first step is write the given values of the physical quantities which are given in the problem. So I have marked it in yellow. So if we start writing, mass of the cylinder is 20 kg, angular speed omega is equal to 100 radian per second, radius is of the cylinder is given 0.25 meter. So step 1 is all writing, summarize the sum and writing all the known physical values, physical quantities. So step 2 is find out the value of moment of inertia. Fine. The moment of inertia of a solid cylinder is I is equal to mr square by 2. So putting the values of m and r, we get the final value of moment of inertia. Third step is find the kinetic energy. So putting the formula for kinetic energy, where uh, moment of inertia and angular velocity is known, that is half I omega square. Putting the values of I and omega, we get 3125 joule. Step 4 is find angular momentum. Angular momentum L is equal to I omega. Putting the value of I and omega, we get 625 joule second. So this is the solution. Let us move to the next question. So let us see the next question. Next question is 7.13. So 7.13 A, let us see the A part. A child stands at the center of a turntable with his two arms outstretched. The turntable is set rotating with angular speed. So angular speed is given 40 revolution per minute. How much is the angular speed of the child if he folds his hands back and thereby reduce his moment of inertia by 2 upon 5 times the initial value? Assume that the turntable rotates about without friction. B part is show that the child's new kinetic energy of rotation is more than the initial kinetic energy of rotation. How do we account? So how do we account of this increased kinetic energy? So let us see the solution one by one. So this can be solved in different steps. So first step, what we'll do, we'll write the physical quantities given in the problem. So initial angular velocity W or omega 1 is equal to 40 revolution per minute. Final angular velocity is omega 2. The moment of inertia of the boy with stretched hand is I1. The moment of inertia of the boy with folded hand is I2. According to the question, the two moment of inertias are related as I2 is equal to 2 by 5 I1. Now, in the step 2, what we'll do, we'll evaluate the angular velocities. So, since no external force acts on the boy, the angular momentum L is a constant here. Hence, the two situations we can write is L2 omega 2 is equal to L1 omega 1. Omega 2 is equal to I1 by I2 upon omega 1. So, putting the values of I2, we get I1 upon 2 by 5 I1 multiplied by 40, that is 5 by 2 multiplied by 40, we get 100 revolution per minute. So this is the answer. Let us see the B part, 7.13 B part. So equate the initial, step 1 is equate the initial and final kinetic energy. First we have to find the initial and final kinetic energy. Final kinetic energy is equal to 2.5 and initial kinetic energy 2.5 that of initial kinetic energy. Final kinetic energy of rotation EF is equal to half I2 omega 2 square. Initial kinetic energy of rotation is EI is equal to half I1 omega 1 square. So upon dividing, we get EF upon EI is equal to half I2 omega 2 square upon half I1 omega 1 square. So putting the values of omega 1 and omega 2, we get 2 by 5 I1 by I1 100 square, I1 40 square. So upon solving, we get EF by EI is equal to 2.5. That means EF is equal to 2.5 E1. The increase in rotational kinetic energy is attributed to the internal energy of the body, of the boy, internal energy of the boy. So finally we came to a conclusion that the increase in rotational kinetic energy is attributed to the internal energy of the boy. Now let us see question number 7.14. A rope of negligible mass is wound round a hollow cylinder of mass 3 kg and radius 40 centimeter. What is the angular acceleration of the cylinder if the rope is pulled when with a force of 30 Newton? What is the linear acceleration of the rope? Assume that there is no slipping. So let us see the solution. So this can be solved in few steps. First step 1 is write the given physical quantities. Mass of the hollow cylinder M is equal to 3 kg. Radius of the hollow cylinder R is equal to 40 centimeter, that is 0.4 meter. Applied force F is equal to 30 Newton. So these physical quantities are given. So we have written that. Now in step 2 we'll find the moment of inertia. So the moment of inertia of a hollow cylinder about its geometrical axis is I is equal to mr square. Putting the value of uh, m and r, we get 0.48 kg meter square. Now in step 3 we'll find the torque. So we know tau is equal to F into R. Putting the value of F and R, we get 12 Newton meter. And the fourth step, will find the angular acceleration. So angular acceleration alpha is equal to tau upon I, means torque upon moment of inertia. Putting the value of torque and tau and I, we get 25 radian per second square. Now find the linear acceleration. Linear acceleration is equal to r into alpha. Putting the value of r and alpha, we get 10 meter per second square. And this is the solution. Now let us move to the next question. So let us see question number 7.15. To maintain the rotor, to maintain a rotor of a uniform angular speed. So uniform angular speed is given, which is equal to 200 radian per second. An engine needs to transmit a torque of 180 Newton meter. Torque is also given. What is the power required by the engine? First we have to find the power of the engine. So let us see the solution. So step 1, we'll write the known physical quantities. So angular speed of rotor is omega is equal to 200 radian per second. Torque tau is equal to 180 Newton meter. Step 2, find the power. The power of the rotor P is equal to torque tau multiplied by angular velocity. So P is equal to tau into omega. Putting the value of tau and omega as 180 and 120, we get 36 kilowatt. Hence the power required by the engine is 36 kilowatt. So this is the end of today's class. Before we close, we request you to subscribe, like and share our channel among your friends and relatives. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Thank you very much for your support and watching our videos. Thank you.